Okay, so if you were with me in the last video, we went ahead and we found the proportionality constant, or in other words, the decay rate of this radioactive potassium, given that the half-life is 1.3 billion years. Now, this growth rate, this is probably not the nicest thing to put into your calculator or to even use this entire thing with our calculations. So I'm going to show you a little trick. We're going to store this number in the variable x. So let's go to our calculator, and what I want to do is I want to go ahead and type in that number. That was the natural log of 1 divided by 2, close the parentheses because that's all we're taking the natural log of, and then divide that by 1,300,000,000. 1, 2, 3, 4, 5, 6, 7, 8 zeros. Let's get that number. That's a very, very, very small number, negative 5.3 times 10 to the negative 10 power. But what we're going to do is, rather than writing all that out so that we can maintain all those decimal places, I'm going to teach you how to store this in X. You have a store button that is right here. It's just above the on. If you click the store button, you see it brought up A and S for answer. Into, we're going to hit the variable key X and then hit enter. Now, every time that I hit X, it's going to have that number. Now, this does not affect your graphing at all. In fact, your calculator understands the difference between the variable in an equation, meaning like in a graphing situation of x, that it could be anything, and using x as a letter in a calculation. It gets the difference, so you don't have to worry about the next time you type something in your y equals it using that as the x value. It won't. Okay, so let's go back to our notes here so that I can finish this problem off. Okay, it says if 10 grams are present now, how much will be present in 100 years and then in 1,000 years? Okay, so our problem, remember, was A equals A naught e to the kt. Well, we want to figure out how much we're going to have after some period of time, so A will equal, they told us we're going to start off with 10 grams times e to the, we just stored that k value as x in our calculator, so I'm going to use that as x, times, and they want to know what happens after 100 years. Now this can be typed in on our calculator as is. Just make sure that you put that entire exponent as a parenthesis. So I'm going to type this in as 10, and then e, I'm going to do second ln to get e raised to the x, because that's where we stored this number at, times 100, and close the parenthesis. So it will take this many years, I'm sorry, after 100 years we'll have this many grams left. Sorry about that, got a little ahead of myself. So our amount after time is 9.999999467 grams. Not a lot happening in that 100 years. Well, let's see what happens after 1,000 years. We're going to have the same situation. We have the amount after time equals, we're starting off with 10 grams, e to the x times 1,000 power, because now our years are 1,000. So let's go back to our calculator. And here again, I'm going to show you another little trick. If you hit second and then enter, that brings back up the last thing you typed. And now we can just arrow over and add a 0. So after 1,000 years, we're going to have this much left. It's not going down very quickly, is it? Well, if you think about it, that does make sense. This would be 9.999994668 grams. If it takes 1.3 billion years to get half of what we started, 1,000 years is just a drop in the bucket.